Bugs and liquids are not in the equilibrium expression.
Do we write it as concentration or pressure?
It doesn't specify, so
Whatever.
yeah, let's just do concentrations.
That's really, yeah. Wow, not even. I was acting very.
All right, this first one. Does that make sense?
Let me see. Yeah, it makes sense.
Okay, let's talk about why some things are in equilibrium expressions and some things aren't. Yes, you can just memorize, don't do pure solids and liquids, and you'll probably get most things correct. But I think if you understand it, it helps with the why questions later on. What is this reaction?
It's a combustion reaction.
Methane combusting in oxygen. Does everybody see that? So it's your Bunsen burner. Okay? Methane and oxygen are making CO2 and water. Okay. The water as a liquid is no longer moving in the same area that the gases are. Does that make sense? So collisions that are going to happen that drive it back, which I'm going to be real honest, this is a huge K value. This reaction is almost completely to the right. Okay? Not a lot of methane gets reformed after you burn it, but it does. So, but the water, if you imagine as a drop, is going to fall out of the place where everything's colliding, and therefore it's going to be kind of removed from affecting that equilibrium position. Does that kind of make sense? Okay, so it's not involved. Now, immediately after it burns, like the instant it happens, that water's still a gas. So within the flame of the Bunsen burner, your K value actually is a little different and shifted, back, and you are actually getting methane reforming. They're never going to ask you that, but that's really what's happening. But it's still very, very shifted to the right. Okay, next one.
Yeah.
And then O2.
Yeah.
But I don't
Okay.
know if it would be to the zero, or like over zero, over one, over infinity, over I don't know.
Over one. Just normal.
Okay. This is a decomposition reaction. Okay. It's falling apart. This again is kind of falling out of where the reactions happen. And it makes a little less sense when we're dealing with solids and gases, but when we get to the bottom of this page, it will make a little more sense when we start talking about that. Okay? 3?
It would be, well, see.
Yeah, good luck writing.
Yeah, that one.
Okay.
I have a question.
Yeah.
Why in the C4 and the first sentence K, and then it's KB, and then it's KSB?
Okay, let's see if we can answer that. This was beautiful. Anyone want to take a guess at what's going on here?
Nice. Exploding.
Isn't it X?
Yeah.
This is one where looking at this might help, the state of matter.
Oh,
Oh,
the
it's,
liquid and the liquid.
Okay, it really does look like dissolving, but I'm just going to go
Oh,
ahead
it's
and
an
give up
acid-base
the
reaction.
ghost here. Number 4 is dissolving. But you're really close. What'd you say?
Acid base.
Okay, it's related to acid base.
It's called.
What you have is disassociation. Okay? So what we have here, and this is, it's funky, and I'm going to tell you, I can't remember ever seeing something like this on the actual IP test. It's possible, it's within our purview. You have here something dissolved, okay? It's already aqueous. This isn't technically like a weak base problem, but the reason it's KB is we are kind of dealing with the disassociation of a weak base, okay?
Oh, okay.
But this base is already dissolved, and it's not disassociating upon dissolving. A weak base can dissolve in water and be in solution, but still be stuck together. And if you guys remember, acids and bases, there's like 3 different ways to think about them, but one of the ways we can kind of deal with it is that bases accept protons and acids give off protons. And then another way we can think about it is the Arrhenius definition, where an acid gives off an H+, which is still a proton, or a base gives off OH-, which is called hydroxide. Okay? And so this is a really funky way to do this. If I was handling this kind of situation personally, I deal with it the third way, which we'll get to in the next unit, called Lewis acid and base. But what's basically happening is, in solution, while it's already dissolved, it actually can react with water. And you're gonna hate this. What did this do?
It upset a person.
It accepted a proton. Do you guys see that?
Oh, it's
The water lost an H.
so it's not water.
So it's
The H got attached to this guy. No, it's a base because it accepted a proton.
I forgot that.
I know you have, and that's what I'm holding to. I'm saying this is also a weird way to write this. This is not normal. Okay, so if it wanted to go even a little worse, we can think of the water, which is a new term for you, amphoteric. The water is actually acting like an acid because it's giving off the H+, if that makes sense. But what's happening here is we have a base that is making a base by turning the water into the base. If that makes sense. It's accepting a proton.
I did not comprehend anything you just said.
It's fine. We'll get to it in acids and bases. But why is the water not in the equilibrium expression? Because it's a pure liquid. Okay, the bottom one is going to be the most important. If we take silver nitrate and we put it in water, we don't care about the water, but we get this disassociation, and that is called KSP. This is going to be a pretty important thing. I'm going to tell you this in my old notes, like how I used to teach this. I did general equilibrium, what we've been talking about. I would do that for like 2 weeks, and I would spend an entire week on KSP because it's that big of a deal, and the problems aren't that much different, but you use it a lot. And then we would move into equilibrium with acids and bases. So I'm interspersing it now, so I'm going to try to throw this in. This solid actually does not affect the equilibrium position. Okay? So when we get this statement, all we have is concentration of aluminum ion.
Do we have to grade the charge instead of the concentration, like for the name, like the 3+?
I'm not going to count off, but yeah, that's where it goes because your exponent is the coefficient. It would get kind of messy out there. Does that make sense? If you wrote the charge out there, that would look like -3 when really
It's
it's.
because I didn't grade the charge, so.
I get you. So are we okay with that? Okay. What does it mean that this isn't in this expression?
That it
There's
doesn't matter
there's
its
nothing above.
concentration.
Okay. We would be below because it's a reactant. But yeah, it makes the expression simple. But what does it technically mean if you're adding aluminum nitrate to water?
Oh, it just keeps reacting.
It cannot go back. No.
Doesn't matter how much you have.
Yeah. It doesn't matter. It's concentrated.
Does that make sense? I could put 5 pounds of aluminum nitrate into a liter of water, and the same amount of aluminum ion and nitrate ion is going to get made as if I put in a gram.
What?
Okay. I didn't.
No, okay. If I have a liter of water, I can put a big scoop of aluminum nitrate in, and then another liter of water, and I can put a teaspoon of aluminum nitrate in, and the concentrations are going to be the same.
Concentrations. Okay. Yeah.
I don't comprehend.
Yeah. Okay.
I will have a bunch of extra aluminum nitrate sitting at the bottom of the container, but what actually will dissolve is independent of how much I put in.
Okay.
Does that kind of make sense?
Yes and no.
Okay, this is a huge implication, so I'm going to beat this one to death. And my former students always make fun of me for the, but why? But why? What does that mean?
What does what mean?
I can put more and more of this in, but the aluminum and the nitrate concentrations don't change.
I don't know. It's not affected. No.
Okay, let me look at it a different way then. If this is the case,
Okay.
and I have aluminum nitrate sitting in my container, if I do something that uses up the aluminum, will that affect the concentration?
It will.
Yeah.
Does that make sense to you?
Yeah.
So if I put in, I don't know, chloride ion, let's say I pour in hydrochloric acid. The chloride is going to react, well, actually that's a bad example. Let me say I put in hydroxide, is a better one. Let me say I put in a base, potassium hydroxide, okay? The hydroxide is going to attach to the aluminum and make aluminum hydroxide. And that's going to fall out of solution as a solid. As this decreases, I'm going to want to maintain this, so more will dissolve.
Oh. Okay. I think I get it.
Does that start to make sense? If I change either of these two values, my reaction will shift to recover that proportion.
Oh.
Does that make sense?
I think so.
So when I have a KSP value, and this is why it's such a big deal, it doesn't matter how much of the salt I add, this amount is going to form, period. Okay? But as I use one of these up, or get rid of it somehow, that causes the reaction to shift. So let's talk about weak acids. A weak acid is going to have this same KSP situation. It doesn't matter how much of the weak acid I put in solution. The only part that disassociates.
Could they were bonding worksheet? Can I grab two?
So if this is a weak acid, it doesn't really matter how much I put in. It will hit its equilibrium position. But if I don't know, put Richard's finger in the beaker, and the H plus starts reacting with his skin, immediately, to maintain the same K value, more of this will disassociate.
Okay. I see it. I think
So
I see it.
when we say weak acid, there's this mental image of, oh, it's not that strong. That's not really what it means. It means not all of it splits into H plus and whatever the other ion is. But just because it's not there that instant, if something's reacting with the acid, more H plus keeps getting made. Does that make sense?
Yeah.
I don't believe.
What that ends up giving us is really weird things. When we titrate, which again, we'll hit an acid base, this is so weird to do it this way. When you titrate normally, if you start with a base, as you titrate, you end up with something that looks like You start at any base, and very quickly the pH changes. Okay.
It's actually not bad.
Okay. But with a weak acid, you end up kind of just doing that. Because this whole time, as you add more acid or more base into your weak acid, more and more keeps splitting off. Does that make sense?
To keep the same concentration.
To keep the same concentration of, in this case, it was a weak base, OH minus, it slows the change, I guess is a good way to put it. And this leads us to something else. And again, I'm just kind of giving you a quick preview. We can actually take a weak acid or a weak base and mix it with the salt of itself. So acetic acid is a weak acid. It's vinegar. But I can make a solution of vinegar, acetic acid, and sodium acetate, the salt of acetic acid, and that will actually buffer it, and it's really hard to change its pH. And so buffered solutions stay at 1 pH, whenever you set it at by the mixture. Biologically, that's massive. You're breathing and inhaling oxygen, but what are you exhaling?
Carbon dioxide.
Does anyone remember from Bio 1, which I know was a million years ago, but is anyone here in Bio 2? You are?
Yeah.
When you have carbon dioxide dissolved in water, what does it make?
Carbonic acid.
Huh?
Doesn't it make carbonic acid?
Carbonic acid. You guys remember that? At one point you had a lab where you put phenolphthalein in water and you blew through a straw and it ended up changing the color.
Oh, my bio got cut off.
Oh, well, okay. Well, that's a normal bio lab, okay? And what you're doing is you're blowing carbon dioxide in the water and you're making a weak solution of carbonic acid, okay? That forms in your blood plasma. So as your cells respire, they're using oxygen that was brought there by the blood, and they're using sugar that came from your food, and those cells are producing carbon dioxide and energy, right? Making phosphorus pop on and off, ATP and the Krebs cycle, citric acid cycle, the whole nine yards. Okay, but that cell makes carbon dioxide as a waste product. That waste product then goes back through your bloodstream to your lungs and you exhale. Does that make sense? Carbon dioxide comes out. If something starts going wrong, like let's say I don't let you breathe, what do you start to feel?
Pressure.
Like-
Just suffocation. A little not feeling of gag.
Like terror,
Yeah.
right? Have you ever swam underwater, like across the pool? Did anyone have to do that? Anyone here a lifeguard have to take that awful
No, I
test?
took swim class.
Okay. You really start getting scared. That is literally your body sensing too much CO2. There's a reason for that. You don't have a low oxygen sensor, you have a too high carbon dioxide sensor,
right.
because very quickly that extra carbon dioxide becomes extra carbonic acid, and very, very quickly that starts interrupting all cellular processes. That lower pH starts wrecking everything. Your actual circulatory system can get damaged in minutes.
Oh, I should stop doing that then.
No, it's totally fine as long as you can maintain consciousness. But it's when you pass out and breathe in the water, it becomes bad. But like if you have a heart attack and your blood stops circulating, that's some of the damage that's happening.
Yeah.
Is you have all this CO2 building up. Now, you also have brain cells not getting oxygen, and that's obviously pretty bad too. But there are illnesses, and there are like lung infections especially, that make you not exhale CO2 as well.
Like sickle cell?
No, sickle cell you don't carry the oxygen well.
Ah,
That's
okay.
totally different. Sickle cell, does anyone know what that is?
Yeah, it's like a deformity in the
In the red blood cells, they end up being like moon-shaped, and it's a recessive genetic trait
What happened to the year of a pathology?
Well, because he brought it up. But anyway, it's really amazing though. No one can figure out why it was still around. But if you have one of the alleles, not two, you actually have some malaria resistance.
I have no idea what
You said if you saw?
Forget the sickle cell. Anyway, if you start getting sick, especially with a pulmonary disorder, okay, one of the first tests they do in the hospital is your blood pH. Because if it gets off by not much, you have minutes left, okay, and they have to fix it. Your blood pH has a buffered system. You have acids and their salts working inside of you to keep the pH the same. Does that make sense? If you're so sick that the extra carbon dioxide is producing too much carbonic acid, there's something seriously wrong, and that's when you get an IV and they start pushing salts and other things to get that buffer back. So this concept of KSP is huge biologically. Okay, let's keep trucking. Yeah.
Explain to me again, like why it's like just a sudden change in the pH instead of just.
That has to deal with how titration actually works and what we're doing, and the fact that it's a logarithmic scale.
Some of
That
my
makes sense.
friends have been posting themselves hold their breath for long enough to get knocked out.
That's not good.
They just
Is that
And then
That's
it's
a
like,
pretty amazing skill to be able to
they
feign.
just faint. And then
Are
they're
they-
going down for like 2 seconds, and then they're like, what the fuck, did I just pass out?
Are they physically restraining themselves?
They're like holding their breath.
That's pretty actually impressive. Yeah, it's brain damage.
Honestly, if you do that, you already have brain damage.
That's just so stupid.
It's funny though.
Like, you know how people will inhale helium, make their voice squeaky?
Yeah.
Doing it once, not that big of a deal.
Good.
Doing it over and over and over again, the helium's not hurting you. The not getting oxygen to your brain is hurting you. Okay? Doing it once, yeah, 10,000 brain cells die, you have billions. Doing it, for half an hour straight, that starts getting dangerous. But the one that's really bad is, I don't know the modern name for it, but people do nitrous oxide.
Nothing make your mouth really deep.
Names.
What?
Names.
Nangs?
Yeah.
Okay. The problem with that is half the high is literally coming from you're just killing brain tissue. The nitrous oxide, most of it is your brain's dying, and that feels good.
Why the cackle though?
It's funny.
Of just brain cells dying?
Yes.
It's pretty horrible. Anyway, but that one people overdo all the time because they end up passing out, and if you have enough of it in your system, when you pass out, your diaphragm relaxes, and so you don't get all of it out. And if you're breathing shallowly while unconscious, you're just killing brain cells because there's nothing but the nitrous oxide and carbon dioxide in your system. Okay, are we good? The worst, the scariest is people who sniff solvents. You ever heard of that?
No.
Like glue.
Oh, you mean me in like elementary?
That wasn't the same thing, but
I see ants.
Bro, why the
Because I don't have many students who are missing them.
That's unrelated to the tweet.
She used to eat ants, used to sip glue.
I don't do that. It's
It was
related.
Elmer's already sometimes, right?
I've had ant candy.
No, but like just pick
Just
the
like
ants off
fucking
the ground.
AirPods.
So next to
Have you not learned that eating food that isn't supposed to be eaten
Apparently, I
causes
never-
viruses?
Hey,
I never ate the red one, okay? 'Cause
Yeah, well,
they're
African kids can't eat anything
They're
else.
spicy. No one told me they're spicy.
I'm sure that we're appetizing them freaking rocks.
I will, in all seriousness though, snails,
oh,
never eat a snail.
Why? Did you?
There is a specific parasite in snails that goes into your brain and there is nothing they can do.
I don't think you can transfer the human though, right? I never eaten escargot.
Oh yeah, escargot I eat all the time. But that's like raised snails,
Yeah.
etc. But there was a kid not too long ago who had heard about escargot. This is like somebody your age. And like on a dare, just picked a snail up like on his back patio and ate it. And normally I later, he was having all these problems, and they x-ray his brain, it's full of these little worms.
Wait, what about like if you buy like professional escargot?
That's totally fine. That's raised, and it doesn't have asparagus. Like I said, I eat escargot all the time.
What is escargot? Can you say it again?
Escargot is just snails cooked in butter.
What?
Escargot is just snails cooked in butter. It's exquisite.
It's pretty good.
Okay. I don't feel around.
I don't eat them anymore, okay? When you stop?
Anymore.
Oh my god.
What made you think that was a good idea?
No, something.
Alright.
Why?
Real quickly.
I wasn't even doing this. I was.
Let's keep going. On page 5, this we talked about. It makes sense. Small k means that the stuff on the bottom is a big number, and the stuff on the bottom is a big number since the reactants go on the bottom. Obviously, the reaction favors the reactants. Large K, the top is favored if it's a big number. The top is where the products are, so the reactant favors the products. And then I don't know why it's written again exactly the same way, but it is. Okay. The reason I'm saying note this well is this is a multiple choice question freebie.
What does it mean by small and
Freebie.
large?
Okay, I'll talk about that in a second. So if you think about it, K, concentration of the reactants over the concentration of the products, right? If this number is like 1 times 10 to the negative 18,
That's big. Or small. But
that's a really tiny number, okay? What does that mean over here?
It's heavily favored by the product.
That is
There's
so,
a whole lot of products and very little reactants left.
so,
Does that make sense?
so it goes forward.
So yeah, the reaction is going to go from reactants to products. It's going to go. If the answer, your K expression is something like that, that means you have a ton of reactants at equilibrium and almost no products. So what's being favored is the reactant side.
So, yeah.
Okay, now remember, these are temperature related too. So if my reactants are iron and oxygen, and my product is rust, in this room, what's favored?
Iron.
Iron and oxygen or rust?
Rust.
No, rust. If you have a piece of metal, like just iron, sitting in this room, every summer they turn the air conditioner off, it gets really humid in here, it's going to start rusting within, weeks to months. Like raw iron rusts really fast. Okay, you rarely see it these days because it rusts so quickly. So the rust is favored. The rusting reaction, iron and oxygen turns into rust, has a K value like this. Most of the, like at room temperature. But if you put rust into a blast furnace and it's 2,000 degrees, you actually lose all the rust and make a bunch of iron. So we've switched where the equilibrium position is by changing the temperature. Does that make sense? Okay. Okay, list of K values, nothing's super exciting here. Okay, Ka values we will get into a lot with acids and bases because you can actually tell a lot from the Ka value. As a matter of fact,
So why A? What does it mean A?
Hmm.
Why A? Like K A.
the equilibrium constant of an acid.
Okay.
So, the Ka value
And
Yeah, it does.
actually equals the pH when you are halfway to your equivalence point. I'll get with an S basis, you don't need to write it down now. But we can actually use the Ka value to help determine the pH in a certain situation. Does that make sense? So it gives us, I don't know, an insight into the power of that acid, how much H plus it's going to produce. Okay, so let's look at, I don't know, let's let's just do HF because it's the easiest to look at. Look at this reaction. Can you write the equilibrium expression for this? Ka would equal what?
Would be concentration of
Oh, so it would be
HO3H3. Oh, wait, okay.
so reactants of products, so it'd be HF over. Wait, no, let me think. Over is.
I'm sorry, it's products over reactants.
Oh.
Yeah.
I don't know how I did that.
First one would be H3O. Okay, I forgot which one we're doing.
So it's gonna be concentration of H3O, concentration of F over a concentration of HF.
Are we okay with that expression?
Yes.
Okay. This number is 10 to the negative 4. Let's forget the first number. It makes almost no difference. 10 to the negative 4. When you have HF dissolved, what do you have more of? F minus or HF? Does that make sense to you guys? Yes? Okay. F minus is going to be the same as the H3O plus, correct? The hydronium? This is what makes an acid an acid. This is the H plus. It's just water with an H plus in it. There's a little plus here. Okay? Are we all okay with that? Okay. The bigger this exponent, the more H plus goes into solution. So, chlorous acid with a 10 to the negative 2 is going to be a stronger, like more vigorous, weak acid than HF. Does that make sense? So the Ka value is telling me how strong these acids are. If I come down here and look at phenol, this is a really weak acid. Does that make sense? Very little H3O plus gets made here. Because its equilibrium expression is going to be the same as this, just with different letters in here. So with a number this small, the bottom is really big, these are really tiny. Does that make sense? Okay. So, if I was going to dip you into a vat of acid, and I told you it was going to be 1 molar, and that doesn't sound like much, but 1 molar of some acids is pretty nasty. You would much rather be dipped in 1 molar phenol. Actually, you wouldn't, because that's a percentage. Bad example, but you get the idea. This would do much less damage than this would, because this is making less H plus. Does that make sense?
Yeah.
Okay.
Wait. So,
Okay, so let me say this. Let me say it again. Do you get it would be much worse to hold your finger in 12 molar hydrochloric acid than it would be 1 molar hydrochloric acid?
More painfully to it, right?
It's more concentrated. And what in an acid's doing damage is the H plus.
yeah.
Or H3O plus, which is the same thing. Okay. So everybody gets that concentration makes a difference. I could dip your finger in these two, and neither will go to 12 molar, but let's just pretend. And actually, this isn't going to do that much, because even though I have 12 molar of the acid, 12 moles per liter in there, very little
Is produced.
is actually making H plus.
Okay.
Does that make sense? Okay.
Oh, so it's just slow.
If we're close, we're there. Solubility is a equilibrium expression function. So KSP is how we talk about solubility. KSP is how we talk about solubility. And I know someone wants to ask me what the SP stands for.
Something dissolves.
That's a good idea.
Is it orbital?
No. That's good though. Nope. I'm sure I knew it at one point, but I don't know.
Google.
KSP just means how well is it dissolved. Okay. Do you recall doing double replacement reactions, precipitation reactions in Chem 1?
Maybe? No.
Yeah.
I don't remember.
Drop of this, and it gets cloudy.
Mhm.
Drop of this, and it doesn't get cloudy.
Oh yeah, we said with hydrogen.
You did it with a lot of things.
Yeah.
Okay. In Chem 1, and even in here, when we start getting into more reactions, I will say this salt is soluble, this salt isn't. So, if I mix, this even shows up. What's going to happen?
There will be a cloudy.
I don't know, it's gonna be NA, NO3, and then CL,
It will be AgCl. And then NaNO3. Probably.
Okay.
Okay, the solvent.
Does that make sense?
Yes.
Okay. So, what can form?
NaNO3 and AgCl.
AgCl.
Oh, because NO3 it doesn't.
Right. So, ready? NaNO3
Yeah.
dissolves. So, just because I mix these together doesn't mean this actually forms, because it doesn't. Now, can I get NaNO3? Yeah, I have a bottle of it in the back. They make that solution, and then they literally have to boil the water away to get NaNO3. Does that make sense? You have to remove the water, because this is incredibly soluble. Does that make sense? So this really, in the beaker, stays like that. Na plus and NO3 minus, and it's dissolved. This, I would have told you in Chem 1, is insoluble. It forms a precipitant. The water gets white, cloudy stuff, and if I let it sit, it rains to the bottom and makes a layer of actual silver chloride. Are we okay with that as a concept? Okay. That's a lie. Silver chloride does dissolve. Silver chloride has that as a KSP value. That means that the ratio of products to reactants is really tiny. Does that make sense?
From other reactants, we have a little bit of products.
Okay, ready? Here's the part you're going to kind of hate.
I already
With the acid, this is soluble. HF dissolves. Does that make sense? So it's part of this equilibrium expression. This is just straight dissolving something. KSP is just the positive ion.
Oh, because it's solid, it's no more part of the.
Yeah.
Okay.
AB is a solid. It's not part of the equilibrium expression. These two are aqueous, and I can measure the concentration. Does that make sense? So if KSP is a small number, like 1 times 10 to the negative 10, that means very little of this dissolves. Does that make sense? Are we okay with that? Okay. AgCl is insoluble. No, it's not. 1 out of every 100,000 dissolves. 1 of every 100,000 AgCls actually splits apart from silver and chlorine ion. That's a small amount, right? 10 to the negative 72.
That's a very small number.
I can have the planet Earth made of solid bismuth sulfide, and I still don't think if we dunked it in the world's largest, or the universe's largest beaker, that even one is going to dissolve. Does that make sense? That is a stupidly small number. Okay, I'm going to go back to acids and bases again for one quick thing, because why not make it hurt?
If it dissolved, would
Make it
it
hurt.
stay
Why not
dissolved?
make it hurt? Seriously.
Yep. Okay, we're going to have to wait 1 second. Okay, ready? KW. Water
It's for water, right? Okay.
It's my dulcet tone. Water self-disassociates.
Okay.
So the water in my Coke here is splitting apart into H plus and OH minus on its own. It's also reforming back into water. Does that make sense? KW is H plus concentration times OH minus concentration.
Without the H2.
H2O is a pure liquid.
Oh, liquid. Okay, okay.
Does that make sense? Okay. Does it make sense to you that every one water has to make one of these and one of these?
Yeah.
So that for water, these two have to be equal. KW is equal to 1 times 10 to the negative 14. What is the square root of 1 times 10 to the negative 14?
I'll have to say it.
1 times 10 to the negative 7?
Thank you, and shame on all of you who didn't immediately see that.
Sorry, man.
Oh, I meant the pH of water. Just that one.
I didn't even hear what you said.
What is it? Oh, for water.
Okay. pH is the negative log of H plus concentration. What is the negative log of 1 times 10 to the negative 7?
7?
7. Remember that?
No.
So, pure water, middle of the acid-base scale, what you're really looking at is the equilibrium constant for the dissociation of water, which, since that constant is 10 to the negative 14th, and these have to be equal, these both have to be 10 to the negative 7. What is 10 to the negative 7? 0 point what?
0, 0, 0.
Can you say it like a fraction?
Oh.
1 over 10 million.
But it's negative.
It's a
that's
numeracy. 10 to the 6 is million. Okay. What that means is that in a glass of water, out of every 10 million is not actually H2O, it's actually H plus and OH minus. Does that make sense? Water's a covalent compound.